Welcome to the module. In last module, we have seen the working of the different subsystems that are involved in order to control the speed of a DC motor. We have also seen the simulation of each and every subsystem, whether it has been meeting our requirements or not. Then we have also seen experimentally how individual subsystems are working, where in order to match with the requirement of the other subsystems, whether that individual subsystem is meeting or not. Now in today's module, we are interfacing each and every system which will be the complete signal conditioning circuit for your DC motor in order to control the speed of our DC motor. Now we will see an experiment on interfacing. Now in experimentally, as it is as it contains so many different subsystems, it is difficult to create the system in a simulation and to visualize it. So what we do is that we use the complete system on a breadboard. Some part will be on a breadboard, some part will be the other board which we have already designed for P, PI and on off controllers. What we do is that by using a pot, we will create a set point. This is the input, which is nothing but a set point. By using the rotary pot, we will create a set point, and the output of the pot will be directly connected to the input of an error amplifier. But generally speaking, the design board has another operational amplifier here, which is nothing but buffer amplifier or voltage follower. The voltage follower is connected between the output of a potentiometer to the input of error amplifier. The reason is that since the output we are getting from the set point is being provided by using a potentiometer resistive divider network, and at the input of an error amplifier again it is connected to the another resistive divider network, there are chances of having loading the input. So in order to not to have a proper in order to not avoid that loading effect, instead of directly connecting it through connecting the output of a potentiometer to the input of an error amplifier, we used a voltage follower circuit. But in this case I have not showed you, but in reality we have designed an voltage follower circuit in the board and we have connected an error amplifier to this. Then another input of the error amplifier, if you see, it is connected from the output of signal conditioning circuit, the second stage of signal conditioning circuit, right. Now the output of this, either we can connect it to P controller or PI controller or PID controller, such that by varying the gains, we can change the gain of a P controller, P gain, and that will be given as an input to the motor driver circuit. But since it is a gain controller, if the gain is really high, there is a chances of getting an output greater than 5 volts. But our motor, as per the specifications of the motor, the maximum rated voltage is 6 volts, and we have designed our signal conditioning circuit to operate from 0 to 5 volts. If it is operating at 6 volts, the RPM of a motor will be higher. Again, the chosen resistance R1 and C1 may not match with respect to that value. So some pulses may miss. So because of that reason, we have restricted our operating voltage to 0 to 5 volts. But since the output voltage of the controller, which is nothing but a manipulated variable, entirely depends upon the error signal that we have and the gain that we set. If the error is higher and the gain is also higher, there is a chances of getting output voltage greater than 5 volts. So in order to not to damage the circuit, we have in practical we have given a Zener diode of 5.1 volt connected at this point, so that even if the P controller output voltage is higher than 5 volt, because of the Zener diode, it provides the input voltage to the motor driver circuit to be only a 5 volt. So the motor will be operating at a very high voltage. So it acts as, one is safety, right, other one is it acts as safety. Then the output of this is given to the motor driver circuit, where we have already seen the working as well as real time demonstration of how exactly it makes the motor to work, everything, analysis as well as simulation. And based upon the input voltage that we have it here, the motor RPM automatically changes and it is linearly dependent. So in order to see at what RPM it is rotating, whether it is rotating at the same RPM as set by the user, we have used an encoder, which is a digital encoder which provides a pulses, and this encoder output is connected to a monostable multivibrator at this point. Since we have not shown any encoder here, I have not given any connection, but in practice there is an encoder which is nothing but a sensor, in our case gives the digital pulses and it is connected to the encoder, even that we have seen that. Then this is our monostable multivibrator, inverting amplifier, and this is integrator circuit which makes the linear output. Then the signal conditioning circuit to match the output of integrator circuit to the input mapping factor, user input mapping factor. So, the mapping factor is approximately 1 volt per 20 RPM. So, if user set the input to be of 5 volts, which means that he is making the motor to rotate at 5 into 20 approximately 100 RPM, right. So, depends upon the what is the voltage set by using potentiometer, the RPM of a motor, it will always control the RPM of a motor to be as per the user requirement. But since the motor is a second order system and we have so many restrictions that motor should not go more than 5 volts and everything, and initially when the input voltage is 5, but the motor initial condition is 0, the error that is given to the P controller will be almost 5 volts. Error will be always this particular value will be 5, and if the gain is somewhere around 2, there are chances of going the output voltage to 10 volts. So, in order to not to damage, so we are restricting to Zener diode circuit. So, such a cases, and when the gain is really smaller, there are chances of getting an offset error. This is called our offset error. Of course, this can be avoided by using PI controller, where the same set point error amplifier, instead of P controller we used a PI controller here. Then this is our motor driver and monostable multivibrator, integrator and signal conditioning circuit. What it changes is, along with the proportional we also have integrating term. I hope by now you understand the importance of having an integrator circuit and have exactly the PI controller eliminates the effect due to the offset voltage, offset error, as well as very fast response. Now, we will see the working of this model. So, if you look into this complete board, so this part is completely the signal conditioning circuit as well as a driver circuit for our motor. So, this is our motor. If you see here, this is the DC micro geared DC motor with attached encoder. So, the RPM of this DC motor is 155. So, it has at the back side, if you observe, it has encoders connected to this. Now, if you see the pin configurations of this DC motor, the top one is the motor input, the bottom which is connected to the red wire M2, which indicates with an M2 is your other terminal of the motor input. So, whereas the second pin is a ground, the second pin here is the ground, and the C1 C2 are nothing but the outputs from the encoder. So, in order to understand whether the motor is rotating in clockwise direction or anti-clockwise direction, by observing the phase shift between C1 and C2, we can estimate the rotation of the motor, and the RPM will be determined based upon how many number of pulses the encoder is giving per minute. The fifth terminal is VCC, which is nothing but the power to the encoder. So basically the max input voltage given to the encoder is 5 volts, and the motor will be the maximum voltage that is required for the motor to operate is of somewhere around 6 volts. So now the design signal conditioning circuit will be used within a range of 0 to 5 volts. When we look into our slide, so recalling the complete closed loop control system, so the input which has to be given, which is nothing but the set point to the system, will be given by using this potentiometer. We can provide the set point required for the complete system, and whereas the next block in that closed loop system, if you observe, which is nothing but an error detector. So this particular block which is implemented using TL072, this particular block act as an error amplifier. So error amplifier basically which measures the difference between the set point and the output from the encoder or the sensor. So the output from the error amplifier, which is nothing but an error, has been given to different controllers here. So this board has 4 different controllers. So the first one is on off controller, the second one is P controller, the third one is PI controller, and the fourth one is PID controller. So depends upon which controller to be used for our application. By using this particular mux, similar to that of mux but mechanically, by connecting the jumpers from the output of an error to different buck connectors here, will decide what type of controller this particular closed loop system is using. And similarly at the outside, if you see, we also have the similar kind of connection where depends upon which controller that the system is using, from the output of this connecting it to the input of the motor driver. So why do we require a motor driver? If you recall, the motor always requires little higher current, and our operational amplifier cannot provide the enough current to drive the motor. So hence, by making use of the output from the operational amplifier as a triggering input to the driver circuit, the current will be drawn from the power supply, but the triggering input will be given from our controller. So as a result, the required voltage will be given to the motor from the input of, based on the input of the controller, but the current will be taken from the power supply. So as we have already seen the working as well as the theoretical understanding of driver circuit, that complete circuit has been implemented using at this particular place. So if you see, this is a transistor which we are using 2N3019, which is NPN transistor, and this is our 56 ohm resistor which is connected in series with in between the emitter of the transistor to the input of a motor, such that it will allow it will not allow higher current to pass through the motor. Similarly, here if you see, this is a TL072, again we are using TL072 in negative feedback amplification mode, basically an inverting mode, so that the voltage that is being applied at the input of a positive terminal will be generated across the output of motor. As a result, whatever the output the controller is giving, the same output will be across the motor, but the current required to drive the motor will be taken from this transistor, and the output of this, the output of the operational amplifier is connected to the base of transistor by using another resistor here, which is 180 ohms to 220 ohms. The only idea of having this resistor is to limit the current flow through the transistor. Then this part, if you observe, this part we have another TL074 which is nothing but a quad operational amplifier. In that quad operational amplifier, this side we are implementing monostable multivibrator. If you recall the importance of a monostable multivibrator, what we have discussed in the previous module. So you understood that the importance of having a monostable multivibrator such that it can convert the encoder pulsing output to the analog output voltage. So, in order to get an analog output voltage, the monostable multivibrator, which is being designed based upon the output of encoder, is connected to the inverting amplifier. So, this is the place where we have implemented the inverting amplifier. Then the output of inverting amplifier has been connected to the integrator, so that the integrator will help us to give a constant output voltage. So, whenever there is a change in the RPM, the encoder will give more number of pulses. As a result, the encoder will give us negative slope signal, negative slope output signal, but we have given a set point at a scale factor of 1 volt per 30 rpm. So, if you want to make the motor to rotate at 30 rpm, the input to be provided is of 1 volt, but the output that we are getting after interfacing the signal conditioning will be somewhere around with a negative slope, but we require a increasing positive slope. So, as we have already seen the circuit that we have used in order to convert this negative slope to positive slope with respect to the design parameters of gain as well as an offset, that complete idea has been implemented at this particular side. So, if you recall, if you see the circuit that we have used, it is completely a differential amplifier circuit, whereas the RF, so the RF resistor, which is a feedback resistor, is used to tune the gain such that in order to match the scaling factor of the input as well as the output of the encoder. This particular resistor acts as an R1 resistor to adjust the offset in order to meet the requirements of the input signal, mapping factor of the input signal. So, now, so what we have done is the output error. So, this is the part where we are giving an input, this is the part where we are giving the input to the controller, which is nothing but set point, and to understand what voltage we have given, which is corresponds to the RPM that is required for the motor to rotate, we are using a CRO to understand the voltage applied at the input of set point by using this particular probe. Then the output of an error is connected to a P controller. So, the error has two inputs, one from the set point which is internally connected, other one from the sensor as well as a signal conditioning circuit. By using this wire, it has been connected to this, whereas the output from the P controller is the output from the error has been connected to the input of the P controller, as well as the output from the P controller has given as an input to the driver circuit by using this wire. Now, we will see the working of P controller in order to maintain, in order to control the RPM of the DC motor using by looking into the signals from the CRO. So, let me switch on. So, now we will see by providing different input voltage as a set point to the system, how exactly the motor is rotating. So, what we have done is that the first channel, it has been connected to the output of the potentiometer, whereas the second channel, which is blue in this case, it is connected to the output of encoder as well as a signal conditioning circuit. So, since the digital pulse has been converted into an analog output voltage by using a proper signal conditioning circuit there, so we can directly interface and we can see the input as well as an output responses at this point. So, yellow represents my input, whereas the blue represents, sky blue represents the output. So, let me change the input. The scale is 2 volts, right? Let me change the scale to 1 volt, both the cases. So, this particular line represents a 0. So, what I will be doing is that I will increase the voltage to somewhere around 5 volts. sorry, right now I will go with the 3 volts. So, the yellow line, if you see, it is nothing but the input, whereas the sky blue line represents the output, encoder output. So, now if you see, since we are using a P controller and the order of the system is second order system, and since the gains that we have used is of already at higher level, we can see because of not enough gains, it can be noticed that there exists some offset error between the set point as well as the output voltage. How can we reduce? If we want to further reduce it, we have to increase the gain of operational amplifier in the P controller, but since the board is already fixed, it has been set to a maximum gain, we do not have an option of change it, but we can design the same P controller with varying the gain with increased resistance value, which can go up to further gain, and we can notice it. So, right now it is at 3, so then I will change it to 5. So, as we are working with a P controller, we can see that it is nothing but a proportional controller. So, when we change, when the error is immediately changing, the proportionally the input voltage given at the input voltage across the motor will also proportionally changing. So, because of that, suddenly we can see there is a change in the speed of a motor, but there exists an offset. So, one way to avoid this offset is either by going with PI controller or PID controller. But what happens? What if I go directly by using a P controller changing the gain? The problem is that when you go with the higher gains of a P controller, at initial stage there are chances of providing higher voltage in order to make the motor to rotate to the required RPM, but because of that the current drawn as well as the voltage applied across the motor will be higher, resulting the damage of the system. So, since to protect the motor from higher voltages, the output of controller is connected with Zener diode of voltage 5.2 volts. So, even though the controller provides an output voltage higher than 5 volts, but the Zener diode can regulate and provide the maximum input of the DC motor to 5 volts. The reason is that this DC motor can only operate at a voltage of maximum of 6 volts, above which it will damage. So, because of that reason, we have used a Zener diode across the output of a controller, which is being connected as an input to the driver circuit of a DC motor. So, as a result, even if you further increase the gain of a P controller, you cannot reach to the set point, right. So, let me change to lower value, so somewhere around 2 volts, and see whether it can be operated at 2 volts or not. Now, here if you see, so the yellow line suddenly decreased to 2 volts, still the output of the motor is following the input, which means that it is properly following, it is properly controlling, but it has some offset error. So, we will see how exactly this offset error can be eliminated by using PI controller. Now, what I will do is that the output of P controller, I will be connecting the output of error to a PI controller. Similarly, the output of the PI controller will be given as an input to the driver circuit. So, I have given input to 3 volts. Now, if you observe, the encoder, the motor is rotating very slowly and it is trying to reach the set point. So, here we can see the motor, so which is rotating slowly and it started increasing the RPM of the motor. So, slowly increasing, and at one particular time after reaching the time, it maintains the output of RPM as an input set point. Now, the time taken by the motor to reach to the set point entirely depends upon the integrating factor or the proportionality as well as integral constant that we have given by using the resistors in our PI controller. So, if you want to further decrease the time taken for the motor to reach to the set point, what we can do is that either we can change the gain in a I controller such that it takes very less time in order to reach to set point. However, because of that the initial voltages as well as current drawn by the motor will be higher. Again we should always have to tune the controller parameters such that the voltage applied as well as the current flowing through the motor should not damage the motor. So, here we can see slowly increase after somewhere around 10 seconds, right, the output is following the input, but with a minimum error when compared to that of the P controller. Right now it is almost saturated. Right. So, even the motor is also rotating with the same RPM as the set point that we have considered. So, what is the set point we have given? It is of 3 volts. 3 volts corresponds to somewhere around 90 RPM, because we have given a scaling factor as 30 RPM, 1 volt per 30 RPM. So, 1 volt corresponds to 30 RPM, since it is of 3 volts it is of 90 RPM. So, now the motor is rotating at a speed of 90 RPM. Let me decrease or let me increase to 5 volts and see whether the motor can go 50 RPM or not, but since it is a PI controller, again it requires some time in order to reach the motor to 5 volts, which is nothing but 150 RPM. So, we can see that at this point I have changed. So, at this point I have changed my input from 3 volts to 5 volts, then the motor started rotating at higher RPM. We can notice the motor, you can hear the noise too, started rotating at higher RPM, slowly increasing. Since it is very difficult to understand whether the motor is rotating at low RPM or higher RPM, the output of the encoder has been connected to a CRO. So, here we can observe the motor is started increasing. So, how do we understand? By looking into the encoder pulses. So, in this case, as we have seen about the maximum resistance values that we can go with the PI controller, because of the use of resistance in PI controller board, we cannot further raise the resistance value. Otherwise, we can even go with little higher gains, integral gains, in order to decrease this time taken for the output to go to the set point. But even the values are smaller, we can understand how exactly the integrator controller is working. The concept remains same, but the tuning parameters which is required to make the to achieve the very fast response, right, we have limitation in the tuning parameter because of the resistor. But after 10 seconds it can be clearly observed that if you see the output and input are almost the same, which means that now the motor is rotating at 150 RPM. Even when I suddenly decrease the RPM, because of that time constant, which is because of the integral parameter, integral time constant, it takes 10 seconds even to decrease the RPM from the current RPM to the set RPM. So, let me decrease. I decrease to somewhere around 2 volts. So, slowly started decreasing it, but it will not it cannot suddenly happen because this is not a P controller, it is a PA controller. It has an intelligence, it has to calculate area under the curve, which is nothing but an error curve in this case, in order to provide the proper manipulated variable to the plant. But here if you see, started decreasing, but after some time, because of due to the gains that we have said there, after 10 seconds in this case, it reached to the set point again. Right. So, after almost 10 seconds, here we can see that still the output and the input are having the same magnitude, which means that the error is almost equal to 0, right. But these fluctuations, when you see the output, you can see some fluctuations. This is because of the integrator output. If you further increase the resistance or the capacitance that we use in the integrator, still we can decrease those fluctuations. But however, it is clearly understood that the motor right now, it is controlling based upon the set point, given by using a potentiometer in this case. With this we will close this module. Thank you.